Okay, hi everyone. In this video, we're going to discuss tutorial 12, topics, Huygen's principle and optical path. So this topic is in the physics STPM semester 3. Okay, question 1. The figure shows a point light source P on the ground. Draw the wavefront from P at time t equals to 1 second and then show the direction of the ray. Okay, B. Use Huygens principle to draw the wavefront at time t equals to 2 seconds. Clearly show the construction that you make. Okay, so for the first question, draw the wavefront. So this is point P and then use compasses to draw a circle from point P. So we assume that this is time taken 1 second for the first wavefront. Okay, that is question A. Then question B, we are going to use Huygens principle to draw the wavefront at time t equals to 2 seconds. So clearly show the construction that you make. Okay, so we use the same compasses. Okay, without changing the distance you make between the 2 points of the compasses. So using the same distance, okay, you choose 4 points on the wavefront just now for in A. So choose the 4 points on this wavefront, the first wavefront. Okay, then you draw the wavelet. Okay, there are 4 points, so 4 wavelet. So the distance between the 2 points on for the compasses is same as the first wavefront, the first wavefront. Okay, now next last step is you join all the tangent to the wavelets to form the new wavefront. Okay, so this is the answer for question B. Okay, next we go to question 2. Okay, find the optical path in the following media. Question A distance of 50 cm in water of refractive index 1.33. B, a distance of 15 cm in glass of refractive index 1.50. And C, a distance of 5.0 cm in air plus 10 cm in glass of refractive index 1.50. Okay, so for the first question, for optical path, we use the formula N times D. N is the refractive index, D is the distance in the medium. Okay, so N is 1.33 and then the distance in the medium is 50 centimeter. Okay, so the answer is 66.5 centimeter. Next, for the question B, a distance 15 centimeter in glass of refractive index 1.50. So that's mean 1.50 times 15. So the answer is 22.5 centimeter. And lastly, we have two medium. Air 5 centimeter and in the glass 10 centimeter. So we total up the optical path of the two medium. So the answer is 20.0 centimeter. Okay, now we go to question 3. The figure shows light waves of wavelength lambda traveling from a point X in air to an air glass interface. Okay, so the optical path in air is L. Okay, given L. The refractive index of the glass is 1.5 centimeter, 1.5. Okay, express the optical path L in terms of wavelength lambda. Okay, for the first question, we count how many wavelength we drawn here. So this is one wavelength. So we have second, third, fourth, and the last one only half of the wavelength. So that's mean total we have 4.5 wavelength. Okay, so from 4.5 wavelength, so that's mean the optical path in terms of wavelength is the distance N times D. Okay, refractive index in air is 1 and the distance is L. So the L's in terms of lambda is 4.5 lambda. So that's the answer. Okay, we still use formula N times D optical path, but the N for air is 1, so times the L. So that's mean the L is equals to the 4.5 lambda. Okay, now we go to question B. Question B, the time taken for the light to travel from the point X to the interface equals the time taken for the light to travel from the interface to a point Y in the glass. So x to the interface air glass is equals to the time taken for x to the interface of the air glass equals to time taken from the interface air glass to the point y. So same times travel. Okay, find in terms of L the optical path from the interface to the point y. So from the interface here to point y. So we use the optical path formula, lambda n times distance, and then from the mention here, time taken is the same, so that's mean is equals to the nd in the air, because time taken is the same, so that's mean uh, the optical path from the interface to point y is equals to the optical path from point x to the interface air glass here. So we use n equals to 1 in air, and then times the distance L in the air. Okay, distance traveled in the air. Why? Because the time taken is the same. So the answer is L. So optical path from the interface to the point is equals to L. Okay, next question. The distance of the point Y from the interface. So we are going to find the distance L. So using optic path equals to ND. Okay, so N times the L, this one is in the air. And then the glass distance in the glass will be, N in the glass is 1.5. Okay, 1.5. So you substitute 1.5. And the distance in the medium, this is the distance in the medium. So let's use D as a symbol for distance from the interface to the Y. So D. So we equate them. Why they are equal? Because the time taken is the same. Okay, so now the answer is D equals to 0.67 L. Okay, so that's the answer for B, question B2. Okay, so in terms of lambda, it has the same number of lambda. Just now we calculate 4.5 lambda, so that's mean from interface to the y also 4.5 lambda. 4.5 lambda, and the distance is 0 in terms of L is 0.67 L. Okay, so now we go to question 4. Okay, question 4. The 2-point sources A and B, which are separated by a distance of 30 centimeter, emit in phase waves with a wavelength of 4 centimeter. State and explain whether constructive interference or destructive interference occurs at the following points. Okay, point X, which lies on the perpendicular bisector of the line joining A and B, and then for B, point Y, which is 50 centimeter from A and 40 centimeter from B. So we do A first. Point X lies on the perpendicular bisector of the line joining A and B. So how to imagine this? So we draw point A and B. Okay, so this is the screen. Okay, the screen. And the bisector we draw in between A and B. So the line in between reach the screen here, X. Let's say we name this point X. Given the question for point X. So we draw the ray, and the ray AX, the path of the light A to X and B to X will be the same, because this is a point that lies on the perpendicular bisector of the line joining A and B. So therefore AX and BX is the same path. So that's mean the phase difference at X is equals to 0. Okay, they reach here at the same phase. Okay, so they reach at the same phase, so the phase difference is 0. AX minus BX will be equals to 0. So if you observe the pattern, this point will show the bright fringe, okay, where means that it is a constructive interference occur at X. Okay, so the M should be 0. The order should be 0. Okay, now we do for the next point Y. So point Y is the path given is 50 centimeter from A and another one is 40 centimeter from B. So we do the same method, point from point A and from point B. This is the screen where the pattern of interference occur. Okay, so this is where starting from M equals to 0, just now from A. Okay, now if 50 centimeter A to Y and then 40 centimeter from B to Y, so that means AY will be longer than BY. Okay, longer. So 50 larger than 40 centimeter. So AY, path AY will be longer than BY. So that means the constructive patterns occur here, or the bright fringe shown in the screen here will be at the order uh, m lambda. So we are going to find that m. Okay, the difference between the path is 50 minus 40. Okay, so same phase, that's mean construction, that's mean constructive interference. Okay, constructive interference. So the order will be, so we calculate the path difference first. 50 minus 40, we get 10 centimeter. So the wavelength is given as 4 centimeter. So that's mean 10 divided by 4, we get 2.5 lambda. Okay, in terms of lambda, 10 centimeter is equals to 2.5 lambda. So 2.5 lambda is in the order of destructive interference. Okay, why? Because the destructive interference, we get the order as m plus half bracket lambda. Okay, so 2.5, so that's mean 2 plus half lambda. So the order m is equals to 2. Okay, we get m equals to 2. And the pattern shown or occurs at point Y is the destructive interference. Okay, so that's the answer. Now we go to question 5. Okay, the figure shows 2-point sources S1 and S2 emitting in phase waves with a wavelength of 10 centimeter. So the amplitude of the waves from S1 is 3 centimeter and the amplitude of the waves from S2 is 1 centimeter. So the point A is on the perpendicular bisector of the line joining S1 and S2. So the point B is the first minimum from A. So point B is the first minimum and the point C is the first maximum from A. From A. So maximum B is minimum and C is the maximum. Okay. So assume that the amplitudes of the wave remain constant. Determine the amplitude of the resultant wave at the point A and A, B and C. Okay. So for question for point A, okay, for point A is at the perpendicular bisector of the line joining S1 and S2. So that's mean A here is the same phase, path, same path difference because it is on the perpendicular bisector, okay, of the line joining S1 and S2. Okay, so the path difference will be S1A minus S2A and it will be 0 because same path difference, for same path S1A equals to S2A. So if the same is 0 and in the order of m lambda where m equals to 0. So what happened at A is the constructive interference. So constructive interference with m value equals to 0. Okay, so the resultant amplitude will be amplitude is given S1 is 3 and then S2 is 1. So the constructive, that's mean we use principle of superposition. So the amplitude we plus together, 3 plus 1 we get 4 centimeter. So this is the resultant amplitude. That's the answer. Now we go to question B. For question B, it is minimum. So if minimum, the path difference will be in the form of m plus half lambda. So if we calculate S1B minus S2B, so the first minimum means half lambda. Okay, so the order is m plus half lambda. So the minimum, first minimum will be m equals to 0. So 0 plus half is half lambda. Okay, So if half lambda, that's mean the pattern or interference shows here is the destructive interference. So it's a dark fringe at B. Okay, so M is 0. Okay, so in this case, first minimum, the M is 0. Okay, now we go to and another one, the resultant. So the resultant, that's mean we use the principle of superposition, and this time because they cancel each other, so we use 3 minus 1. The answer is 2 centimeter. Okay, now we go to the question C. Okay, question C is state their first maximum. So for the first maximum, the M will be 1. M will be 1. So M lambda, the phase difference, the path difference, where S1 C, S2C is longer. So that's mean S2C minus S1C. Okay, this one is opposite here. S2C minus S1C. And the first minimum will be M lambda, where M is equals to 1. So I didn't write here. So M equals to 1, 1 lambda. So the what happened there is the constructive interference, and the M order is 1. Okay, here 1. Okay. So the if it is constructive interference, so the amplitude is 3 plus 1, which is equals to 4 centimeter. Okay, now we do question B. Question B, what is the path difference of the waves from S1 and S2 at the point B and C? So the path difference. So the path difference at point C first. So at point C will be equals to M lambda, because M is 1. So 1 times lambda is 1. Okay, and lambda is given as 10 centimeter. So that's mean the path difference at point C will be 10 centimeter. In terms of lambda is lambda, because it happened at M equals to 1. So 1 times lambda, 1 times 10, we get 10 centimeter. Okay, at B, we just now we calculate half lambda, because it's the first minimum. So first minimum, half lambda, half times 10 centimeter. Okay, we substitute the wavelength there. So that's mean the path difference is equals to 5 centimeter. Okay, so that's the answer for question B. Okay, so that's the end of tutorial 12.